So two talks which I feel are related to each other, even though they weren't really presented together at NIP. So there are the two papers, if you can see. So it's a summary of the presentation of Dmitry Krotov and Jimmy Baugh, and collaborators of both of them. Oh, how do I go to the next one? Ah, okay, perfect. Okay, so here's the outline of my talk. So first, I will talk about associative memory. I will tell you how, as you probably know, general human memory works differently than what we're used to with computers, because human memory is associative. So if you think of a croissant, then you all of a sudden think of the Eiffel Tower, and whereas a computer, you need to give it an address, and it goes to this address and figures out this memory. And then there was this, I'm going to tell you how there's this idea that 50 years ago or more, how to implement such an idea using energy by trying to have each memory located at the bottom of an energy well, and then you just flow down there to recover the nearest memory. And so this is all old stuff, but then the paper presented by Krotov at NIPS then tells us how to store, there was a problem that you couldn't store so many memories there, and he figured out a way to store memories more densely. That's where the dense associative memory comes from, because the memories could be stored more densely with the same amount of neurons. And then what he also figured out with collaborators was that by changing the shape of this well, you could alternate between what type of memories you were storing and how you could link that to the recurrent neural networks. And from there, I'm going to skip on to the second talk, which is fast weights, which are an implementation of this idea in recurring neural networks. And so that the networks has some sort of associative memory while it continues. And I'm going to show you how it improved results on kind of typical associative memory, like kind of typical working memory task, how it acts really like some memory task. Okay, perfect. So first, yeah. Human memory. How does your memory work? You see a croissant in front of you, and you think, yeah, like Paris, France, whatever. Computers like this laptop doesn't work like that. To retrieve a memory, you need to give the physical address, the pointer, the physical address in where it's stored. It goes to that location and retrieves the memory, whatever is stored there. It's memory by location of where it's stored, and not memory by content. You don't search by content, whereas your memory searches by content. So one way to try to implement that in computers is to have some sort of an energy well. So here is X is the location of, is like all possible memories, if you can see the graph. And then if I give one random X, the point is if I follow the gradient down to the bottom of the energy well, then I recover the memory which is most closely, like the content which is most closely associated to that. So if I gave you 0.9 here, so I have two memories here. I have 0.1, memory 1, which contains 0.1, and memory 2, which contains 0.8. And if I feed in 0.9 to the system and I walk down the well, then I recover 0.8, which is the closest, kind of the closest thing that I have in memory. So this was implemented a long time ago with Hopfield networks. And the basic idea is to have this equation at the bottom where you have these xi's, they're your memory vectors. Usually they're done with plus or minus ones, only containing plus or minus ones. And then what you do is you put in your sigma, which is your content, which you try to find a memory which is the closest to it. And when it will contract, you do the square of the inner product with the size, and you sum it all over. You sum it all up. If they're kind of random or evenly distributed, or if they're highly dimensional, then what will happen is if it's far away from another one, it will most likely be orthogonal. So it will all go to 0, except for the one where it's the closest to, and then it will, this will do minus the norm of that vector. So you have little holes at each of the vectors, like this, and when you put in your vector, you're close to the hole. And then the idea is to kind of walk down that hole, walk down into the low energy position. So what this group did was, normally you have that with, so F here, it's the same equation, E is equal to the sum of the memories, like the scalar product of the psi's and the sigmas. And normally you use F is equal to x squared. And the problem with that is that you can't typically store a lot of memories, because while typically if you're far away from another memory, if you have your sigma, which is far away from some other psi, it will, if it's high dimensional, it most likely will be orthogonal, or if it's 0s and 1 and they're kind of averaged out, it will be orthogonal, it will be 0. There's still some fluctuation. And oh, it would be great to have a pointer. Maybe I can just like walk on stage. So what will normally happen is that there will still be a little bit of fluctuation in the other one. So if you have too many of them, you will have a lot of fluctuation, and they will bring you out of your memory well. So one way to try to pack in more information, what they did is they used a different potential, not n equal 2, but higher n's. And this makes really steeper walls. So even if you have a lot, so this is the sum from mu equals 1 to k. K is the number of memories. And if for each additional sum you have more fluctuations. But if you have those tight walls in your, like those really steep walls in your well, then you can have higher k. And what they showed was that this equation at the bottom here is that the number of memories you can store is proportional to the number of neurons, big N, that you have, to the power of the shape of your memory well, where your memory well is x to the n, then it's the number of neurons to the power of that n, the exponent of your polynomial. So that's how they achieve these dense memories. And then subsequently, the other thing which they found, which was really interesting, is that so normally when you look at there's kind of this debate of how do neurons in your brain work? Do they encode like a simple feature, like a line? There's some neurons like that, for example, in the first neurons in your visual cortex, they will encode lines or at different angles or something like that. Or do they encode complex concepts? Like, do you have like a grandmother neuron which only fires when you think about your grandmother? There was an article some years back about that being the case. They had discovered the grandmother neuron. So the really, really interesting thing which they found here was that they used this concept on MNIST, which is a data set of handwritten numbers, using these different n's, memory wells. And what they found is when they trained it with n equal 2, the typical thing, then each neuron would encode for very simple features, like you can see here on the left, very simple lines and things which can be used for many numbers. But the more they increased the n, the more the neurons encoded for prototypes. So one neuron would fire for 2s, and one neuron would fire for 6, or so on. You can see it here on the right. So you progressively pass from neurons which encode for very basic features to neurons which encode for some sort of prototypes. Now, why that is, I don't know, and they didn't explain. I have kind of two suspicions, but this is just me rambling on. I don't know if it's true. So one is, could it be that because you have a more squared type well, you really, like if you're similar enough, you just try to avoid the wide differences. So as long as you're similar enough, it's okay. If you deviate a bit from your prototype, it's fine. You just don't want to deviate a lot. So in that sense, maybe that makes it more prototypical. And maybe it's just the fact that there's more capacity for each neuron, and therefore you can just afford to use one neuron instead of many neurons to encode any particular entity. But I don't know. Right. So then the next thing is you can convert this type of math into a neural network by seeing that basically going down into the bottom of the well is moving slightly down the energy function. If you derive it like this, you see you're going down the well. So it's like acting with a layer that acts with the derivative of the energy function. And so therefore we see that if we use rectified linear activation units, which is the typical thing now being used, like the standard canonical thing to use now in neural networks, then you're basically using this this old style associative memory if you use them in Hopfield networks. But you can use this dense memory by using activations which are, instead of being rectified linear, they can be rectified polynomial to the power n. And that's how this group did it with those MNIST numbers. Right. So now I'll go to the next topic, the fast weights. So the issue in the current neural networks is we have kind of two timescales. We have one timescale, which is the activation of the neurons. And like if you have a recurrent neural network, that's where you store your state in the activations of the neurons. And you have another time scale, which is the weights, which is, you run it for the whole time and then you change the weight at the end of a mini batch. So you have these two time scales. But you don't have kind of an intermediate time scale which acts like the working memory, which doesn't change the weights in your brain, but also is longer than the specific activations of all the neurons. So in the human brain, you have neural activations which are on a timescale of 10 milliseconds, but your working memory lasts much longer than that, an order of magnitude longer than that. But it's still shorter. It cannot be encoded in the plasticity of your brain because the plasticity of your brain takes a long time to work, which is like from minutes to hours for the actual connection strengths to change in your brain. So it would be nice to implement that in neural networks, and also it would be nice to implement some sort of associative memory in your neural networks. So how do this other group do that, the group of and Jimmy Ba? So what they did was that they have a typical recurrent neural network, but then at every time step, they use this associative memory. And so A here at the bottom of the screen is this associative memory, which they will use. And they store the previous activation of the previous time step on it, but they let it decay exponentially with a constant lambda here. And what they said in their talk is they typically use a half-time decay rate of 3 to 4 time steps. And so they use this Hopfield network to walk down this I'll go up again. So here you have time step t, and here you have time step t plus 1. Okay, I'm blocking everything. And what you do between time step t and time step t plus 1 is first you put in your activation here in your memory, here. That's this A will act like this T of the associative memory. And then you do n steps of walking down your memory well to recover your previous memories, to look if they might be useful in the running of your neural network. So you recover the previous, you store it, and then you run it to see if what you currently have evokes some past memories, and you potentially use that, and then you go to the next time step, put your current activation in memory, run. Oh, Okay, I'm theoretically finished. I'm almost done. Then you run it again and so on. And what they showed was that this was very useful for typical working memory tasks. So the test was the following. So you have these input strings here. I don't know how many there are, 8 numbers. And then you have a question mark. So that's what they feed to the network. This input string of 8 numbers, question marks, and then a character. And the task is to find the character which came in after that. So they're fed that one by one. So the network is first fed C, then fed 9, then K, then 8, then J, then 3, then F, then 1. And then the question is, what came after C? And the answer was 9. So they trained the network on this sort of task. And they show that their network considerably outperforms other networks on this type of working memory task. So you can see that this is really adds some sort of working memory to the network. So you can see that the LSTM, which usually does a great job for everything, is, at least if you use only 20 neurons, it has like 60% error, whereas they have like less than 2% error. And they even used the modified LSTM that some other group did, the associative LSTM, which also had supposedly have some associative memory in there, and it was also not doing well. So yeah, so with this task, they showed that their network, by using this fast weights, adds some sort of working memory to the network, and it works well for this task. They also showed that it works well for other tasks, but I don't really have time to go into all of that right now. So, just in conclusion, the human brain works with associative memory, so we want a way to do that. That was done a long time ago. But the new thing at this NIPS paper was finding new shape of the well so that you can store more memories. And not only that, but you can interpolate between having more basic feature memories and more prototypical memories. You can convert that to a neural network, and then the fast weight is using these associative memories and putting it into a typical recurrent neural network to add some sort of working memory to that network, which takes a lot of the strain away from the network activations to recall things, because they can just put it in the memory, and which gives then better results. Thank you. And does anybody have any questions?
Do you have any idea or debate about like when you would use this and when would you use an LSTM? Like which kind of tasks are good for this, and like, do you know if like real world results using this?
Yeah. So another case where, okay, so I don't know which case where it would. It's difficult. I guess if you really don't need working memory, then this will just be excessive baggage. But there's other tasks, real tasks, which were using also these fast weights, which were doing better than LSTM. For example, facial expression recognition, or any type of facial recognition when they're using some type of attention-focused things. Then these fast weights do also a lot better than LSTM. They don't yet do better than deep convolutional neural networks. So deep convolutional neural networks still do better at that because they kind of get a whole picture of everything at once. But these, if you kind of use an attention mechanism, then these do better than the LSTM because they have this kind of working memory. I assume that if you have a task where you really don't have much memory, more like if you have some sort of data which comes from some sort of Markov chain, then that's probably not useful, and you might as well use an LSTM.